Hi, we're continuing our talk about the states of matter. Again, our standard: to obtain, evaluate, and communicate information about the structure and properties of matter. This is Lucy. We have 3 Yorkies. She's the youngest, so sometimes she sits with me, so welcome to Lucy. We are going to be doing bubbling over, which in our game board for this year is 3.2E. And the essential question is, how do liquids and gases change state? So we have to go back to that heat curve, there it is again, and our knowledge about what are each of the 3 states of matter. So these graphics aren't going to go away for a while, neither will these definitions. So we're going to be talking about liquids and gases. So a liquid has a definite volume, but not a definite shape. If I took my coffee, there's about probably 40 milliliters left. It takes the shape of my coffee cup. If I pour this on the floor, which I won't, it will still be 40 milliliters of coffee, but it'll no longer be the shape of my mug. It'll be the shape of the floor. Particles can move freely past each other, but they still have a slight attraction to each other. And then we're going to be talking about gases. Gases are moving so fast that they don't have time to really slow down enough to have that small attraction to keep them in the liquid form. So they're buzzing around like crazy. In the air that you're breathing right now, you have oxygen and you have nitrogen, carbon dioxide, other trace gases. So one of your questions coming up is going to ask you, how does air pressure affect water boiling? And so on the left, we have the water boiling at sea level, and we have water boiling on the right at a very high altitude at the top of a mountain. So remember that air pressure is the weight of the air above you pushing down. So just because we can't see it, feel it, capture it, there still is mass pushing down on us. And so that's going to affect the boiling rate of water. The boiling point at sea level is 100 degrees Celsius, and the boiling point high up in the sky is 70 degrees Celsius. So things are going to take longer to cook up in the mountains. On the next slide, we're going to watch Neil deGrasse Tyson talk about how pressure affects the boiling point.
So what happens if I reduce the air pressure? Okay, well, the transition from ice to water is still the same. It's not affected, but the boiling point is affected. As you know, cooking times have to be adjusted on mountaintops because when you boil water, it's not 212 degrees. Depending on the height of the mountain, there's less air pressing down that's preventing it from boiling, okay? The boiling point is not some absolute fact about the water. It has to do with what the air pressure is sitting above it. If you have extremely high air pressure, water has to go to a much higher temperature before it boils. So the boiling point of water that's reported in all textbooks is at sea level, at 1 atmospheric pressure. That's how you get 212 degrees. If you start reducing the atmospheric pressure, it's 210 degrees, 205 degrees, 200 degrees, 190 degrees, 180 degrees.
180 degrees?
No! Yes, and so that's not as hot as 212 degrees, so you got to cook the food longer. All cooking times are increased for this reason.
Boy, that was fast. All done there.
So what happens if I
So, your question, number 13. What would happen to the boiling point of water at 8,000 meters above sea level, where air pressure is lower? Explain your reasoning. So make sure to use words in your explanation like pressure, molecules moving, slowing down, changing state. The next question is a visualize question, and it asks you to, below each box, write the state of the substance shown. So hopefully that's a pretty easy one for you guys to get done. On to number 15. indicate whether the change of state in each process is caused by particles having more freedom or particles having less freedom. So the first picture, you're going to either write A or B, depending on how much freedom you think the substance has. And now we're going to watch this video on contrails. And so this is a verify segment on a news channel where the viewers sent in a question and they verified it. So the question was, those long thin clouds you see behind planes are contrails, not chemtrails.
Airplane chemtrails. It's one of the longest running conspiracy theories out there. Our verified team looks into what airplanes are really leaving behind.
If you've ever looked up to see a plane streaking across the sky, you can't miss the long white clouds they leave behind. Conspiracy theorists claim the clouds are chemtrails, or trails of chemicals being dropped on people below. Videos on social media with the hashtag chemtrails have more than 143 million views. And even today, some people, like Verify viewer Monica, want to know if chemtrails are real. So, let's verify. Our sources are the American Chemical Society, the Environmental Protection Agency, the University Corporation for Atmospheric Research, and a 2016 study into contrails by UC Irvine and the Carnegie Institute for Science. All of our sources say no, chemtrails are not real. The streaks you see in the sky are called condensation trails, or contrails. In case you need more convincing, let's explain how jets fly. Jet engines run incredibly hot at more than 3,000 degrees, but the air temperature at 38,000 feet is incredibly cold, around minus 40 degrees. So when the engine's hot exhaust, which contains water vapor, hits the cold temperature, it turns into ice particles that create the white streak of a contrail. The contrail can last for a few seconds or even more than a day, depending on how moist the air is before evaporating. Numerous studies by the government and independent scientists have found no evidence that chemtrails exist. The most extensive was in 2016, where researchers collected water, soil, and snow samples from 70 places below where contrails were seen. None showed high levels of chemicals. So, no, chemtrails are not real. So, where did the conspiracy theory about chemtrails originate? Many believe it started after the U.S. Air Force released a report in 1996 theorizing that a combat aircraft's afterburners could disperse carbon into the air to possibly camouflage the plane from radar. With your Verify, I'm Brandon Lewis.